Hello, my name is Fonseca-Lopez, and this is Lab 5 of the Falling Slinky. So just a small overview of my presentation and experiment, do a short introduction to the experiment, talk about some of the fundamental concepts applied throughout it, demonstrate the tracker analysis used in the experiment, show the computational model constructed to match the experiment, compare the results of the computational model and the tracker analysis, and then answer some additional questions in the conclusion at the end. So the purpose of the lab is to predict the trajectory of a slinky as it falls while accounting for forces such as gravity and air resistance. The experimental part of this lab, I took a recording of an extended slinky being dropped and analyzed its trajectory using a tracker. The computational model was constructed using GlowScript to observe the slinky falling in perfect conditions. The results of the experiment show that while there are some slight fluctuations, overall the bottom of the slinky remains stationary throughout its fall. So some of the fundamental concepts of physics applied here. We have Newton's second law, which in this case we used to derive the position and velocity update formulas. Then we also had to account for the drag force affecting the slinky as it fell. And then we account for the forces of gravity and the force of the slinky. And in this case, this tension from the slinky is counteracting the force of gravity, which makes it m times g in the positive y direction. So here's just a portion of the tracker analysis. The mass of the spring was 0.2 kilograms. The height of the man on the left was 1.76, which we used to calibrate the tracker analysis. The initial position at the bottom of the spring was 0.0063 in the y-coordinate, and then the initial velocity for the bottom of the spring was 0 across the board, because it remained stationary until the top part of the spring hit it. So here's some of the code from the computational model. In the top left, we set the initial conditions, such as the initial mass and velocity of the spring. In the bottom left, we have the first calculation loop, which calculates the position and velocity as the top part falls while the bottom part of the slinky remains stationary. And then on the right, we have the second calculation loop, which now accounts for the change in velocity and position of the bottom portion of the slinky as the top part has hit it and it is now falling altogether. So just a chart comparing the results of the two. On the left, we have our observed model, and on the right, we have our computational model. As you can see, the observed model fluctuates a lot once the bottom portion of the slinky starts falling, while the model just falls in a straight line. These fluctuations can be for various reasons, such as errors during the tracker analysis, or air resistance that wasn't incorporated correctly in the computational model. But you can see they follow a very similar trend. Bottom part stayed completely stationary first 10 seconds of the video, and then they began falling at about the same rate. So like I said, some possible sources of error. There could have been mistakes while placing tracker points. That's the reason we could see the graph moving up and down at points it shouldn't. And then the real world observation could have been experiencing outside forces, such as we accounted for drag. It could have been incorporated incorrectly into the computational model. So why does the bottom of the slinky remain constant while the rest falls? The forces that are interacting in the y direction, tension and gravity, cancel each other out because the tension from the slinky acts as a spring, counteracting the force of gravity. This makes it so the bottom of the slinky remains stationary until the tension cancels, the tension reaches zero, meaning gravity now affects the bottom of the slinky, so it all falls down together. And what if the slinky was thrown downwards instead of just being dropped from rest? So the slinky would still produce the similar results with the bottom remaining constant until the top reaches it, except that now it would happen faster since we would have more force coming down, meaning the top of the slinky would travel faster and it would hit the bottom of the slinky sooner.